In this section, we're going to be looking at linear regression, which starts with scatterplots, which will be graphing this data using XY coordinates. So with this section, what we'll end up having is two numerical variables. So we'll have this numerical data for two different characteristics or two different times. And what we'll end up doing is calling one of the numerical data values x and the other y. In choosing this, there is a relationship that relates to algebra in that when we choose x variables, x is always the independent variable. So it's often something that doesn't really change based on something else, if that makes sense. Whereas the y variable is considered the dependent variable. So often there's something that could possibly cause an increase or a decrease in that value. There's this relationship of independence and dependence. So what we're going to look at is this data with crickets, and what they did is they recorded the temperature outside and the chirps per second. So to get an idea of this independent and dependent variable, it's this idea of if we think about temperature and what it depends on, it's like, is that going to depend on the chirps per second of some crickets? Probably not. The temperature is probably working on its own, whereas looking the other way around, thinking about could chirps per second be dependent on temperature? Well, that's something we can investigate here to see if there is a relationship where maybe the chirps change based on the temperature outside. So with that, when we get our two columns of data, we can start to think about which is x and y based on which would operate independently and which would be dependent. Independence usually comes through with things like temperature. If we look at anything with time operates independently, something that's not going to change much based on other factors. So creating a scatter plot, what we do is we have this data, and what's key is that when we look at this data, it is lined up across the row, and it's coming from a single observation. So what this first row tells me is that they recorded a temperature of 89 degrees Fahrenheit, and at that time, they recorded 20 chirps per second. So those two data values go together. And then if I choose another one, let's say this one here, in that fourth column, when the temperature was 70 degrees, there were 15 chirps per second. So we can't really mix up the data in terms of the columns because they are paired. So that's where we get this paired data of x and y going together. Now, when we make this, we'll want to create axes like we would in algebra. So we're going to have a y-axis and an x-axis. And with these, we'll typically just be in the first quadrant, meaning we don't really need to put our axes in the middle. Everything should be positive when we look at these, so we don't need to see those other quadrants. So x always goes along the horizontal axis, so what we'll collect along the x-axis is temperature, and then along the y-axis, that will be our chirps per second. And then we just need to set up a numerical scale. So looking at temperature, it looks like I'll need to see like a minimum of below 69. So maybe I'll go and start at 65. And then I need to see up to, I guess, about 95. So what I'm going to do is kind of jump by fives here, but covering two blocks. And that should spread out the data enough to create a clear scale to see. So I just have to kind of think about the numbers that we want to see come up here. Now, when I did this, you'll see what I'm basically saying is like 2 blocks is equaling 5 units. So I set this scale that works across that x-axis. However, I have this little error with my first block. I jumped from 0 to 65 with that first one. So a symbol that you want to use when you do that is just this kind of line break. It just says there's nothing between 0 and 65, so we want to start our scale further along the number line. All right, and then with chirps per second, I guess we want to see a minimum of about 14 and see up to about 20. So I'm going to go ahead and start at 13 and then do units of 1. 14, 15, 16, 17, 18, 19, 20. And that should fit everything and spread it out pretty nicely so we can see it. I did the same thing where I skipped 0 to 13, so I'm just going to throw in a little line break to make that more accurate. All right, then we go and start plotting our data. So with that first measurement of 89 degrees and 20 chirps per second, what we do is we go to 89 along the x-axis. So if we go all the way out to 89, which is out here, and then look up 20 on the chirps per second, and then just draw a dot where those match up. So the coordinate 89, 20 is going to be landing about right here. And then if we wanted 93, 20, so then I would go to about 93, 20, and draw a dot there. So you won't connect these dots. That's part of the name, Scatterplot. It's going to be these scatters of dots. So what I'm going to go ahead and do is pause the video so you don't have to watch me draw every single little point, but maybe try it out for yourself, and then we can see what comes out of our graph. So here's our finished graph. So what we can see is all of our data points plotted here. So what we want to do in this section is look for trends with this data. So we don't want to analyze too closely. You kind of want to step back from it and see, what do you see generally happening with the data? So let's look at the types of questions we could answer. In part A here, it says, is an increased number of chirps per second caused by an increase in temperature? So what we see in our graph is this general trend of, as temperature is increasing, overall the chirps per second is increasing too, kind of seeing this trend that's this positive, it comes down to a positive slope. So as we increase x, y is also increasing in general. What we want to be careful of with the wording here is this word caused. Something that's going to come up in this section is trying to claim causation, claiming cause and effect. So saying that if we increase temperature, then chirps per second will increase too. But we don't know that for certain. There could be lurking variables with this data. Again, way back when in our first week when we talked about experiments, it was that we needed randomization and a control and a treatment group and a placebo if we could, and all of that we could get to cause and effect. This is just observational study. We just collected the data, observed, recorded, and then we were done. So with our data, there's going to be the possibility of lurking variables. So even though we see this trend of increasing temperature with increasing chirps per second, maybe there's something else out there in nature that's causing the increase in chirps per second that links to temperature. It might not be the temperature itself. So with this, no, we can't claim causation. To claim cause and effect, we would need a controlled randomized experiment, which we won't have with this data. So then B changes the wording a little bit. What happens in general to the number of chirps per second as temperature increases? So what we can do is use kind of looser wording. We don't have to claim cause and effect, but we could say, in general, we see these increases happening. Or there's this association, there's this relationship. Basically, we just want to choose some wording that makes it looser and not as strict of cause and effect. So with this, what we could say is, as temperature increases, in general, chirps per second also increase. So some wording you'll see in this section, we could work with wording that says like tends to. In general, as temperature increase, chirps per second tends to also increase. But then like we'll use the wording, is there some like association or relation? But we want to avoid cause and effect. All right, so let's talk about some vocabulary down here. So we talked about y being the dependent variable and x being the independent variable. In this section, we use slightly different wording to relate to linear regression and correlation. So with the y variable, we call this the response variable because it's typically responding to something else. So in our example, that would be the chirps per second. And so that we're trying to see if those chirps per second are responding to our independent variable, which we call the explanatory variable. It's like that would explain some sort of change. So it's that temperature could explain some change in chirps per second. So with that, let's see, our last piece. You can kind of use this wording to help figure out with any data set which is your explanatory, which is your response. Like with our data set, or I kind of described independence and dependence, we could also think about like, does temperature respond to chirps per second, or does chirps per second respond to temperature? And typically one of those sentences will just make a little more sense, and that'll help you tell which one's X and which one's Y. Sometimes it could go either way. Sometimes there isn't an independent or dependent variable, so you just choose one, and either way would be correct. And then our last piece is to be careful of claiming causation. We can talk about predictions or trends, but we can't say anything with causation. So what we're going to end up doing with these is looking at these scatter plots and analyzing how these two variables are related to each other. What's the strength of the relationship? What's the direction of the relationship? So we're going to start analyzing these scatter plots in the next video.